Let us now consider pyrometallurgical extraction of metals and the unit processes that are required to extract metal from the respective ores. Now, what will I do? I will first of all give the general introduction and then I will consider one by one unit process as required for extraction of metal through pyrometallurgical route. Now, as all of you know that ore deposit in the nature, they are either oxidic, either the oxide ores or you have sulphide ores. Now, with this I mean that most of the metal ore deposits, they are either in the form of oxides or in the form of sulphides. The majority of the metals they occur in these two particular form. Now, as you recall that the production of metal involves removal of oxygen from the valuable mineral, that is for example, oxygen from Fe2O3 and then followed by separation of metal from the gangue mineral. Now, whereas in the oxide ore it is easy to reduce the oxide by carbon. I have also mentioned that the reductant should be easily, economically and cheaply available. You can look at the Illingworth diagram, which is a plot of RTLN PO2 against temperature. You can find out which element can reduce the oxide. So, you will note that there are several elements can reduce, for example, Fe2O3, but one element which is abundantly, cheaply and economically available, that should be used. So, in this connection for oxidic ore, in most of the cases carbon is used as a reductant. So, here carbon is used as a reductant. Carbon is used as a reductant. So, carbon can easily reduce Fe2O3, or if we have zinc oxide, then it can also easily reduce and we can get the metal. Now, as regards sulphide ore, there are certain issues. So, as regards sulphide ore, there are problems that it is very difficult to reduce sulphide directly into the metal. First, say hydrogen is not an effective reducing agent, is not an effective reducing agent to produce metal from sulphide. Second, also carbon is also an inefficient reductant, This information you can get from Illingworth diagram of sulphides. Third issue in case of reduction of metal sulphides, that there is a mutual solubility, there exists mutual solubility between metal and sulphides. So, this mutual solubility between the metal which is produced with the sulphide, it makes extraction very difficult. So, therefore, the production of metal from sulphides cannot be done by directly reducing sulphide into metal. So, the route only is that first sulphide is to be converted to oxide. So, therefore, in all pyrometallurgical extraction of metal from sulphide ore, one of the important unit process is called the roasting. This is the most important unit process for production of metal from sulphide ore, and the process is called the roasting. Now, as before I go details about the roasting, it is also important to note that all pyrometallurgical extraction, they require source of energy. So, I give a brief account of source of energy, which is then followed by roasting. So, let me take little bit about source of energy. Source of energy, one, it could be exothermic reactions. Exothermic reaction. For example, S plus O2, that will give you SO2, and delta H naught F at 298, that is equal to minus 70,940 kilocalorie per kg mole, highly exothermic reaction. Or it is also possible formation of sulfur trioxide, and where delta H naught F, that is equal to minus 93,900 kilocalorie per kg mole. Or certain other oxidation reactions, for example, iron to Fe2O3 or Fe3O4, it may also release heat, then FeS to FeO or ZnS to ZnO and so on. They are also the source of production of energy as required for almost all pyrometallurgical extraction. The another source is the fuel. Another source is the fuel, and here one have say fossil fuel and synthetically prepared fuel. Synthetically prepared fuel. Under fossil fuel, one can use coal, oil or natural gas All these fuels can be used for generation of thermal energy, and the secondary fuels or the secondary fuel that could be derived from the fossil fuel. One is the producer gas, and another is the coke. You know, coke, it is used for reduction smelting in blast furnace or production of iron. It is not a naturally occurring material. So, in all these fuel, that is whether fossil fuel or secondary fuel, the energy is obtained by combustion. Energy is obtained by combustion. Now, in all fuel we have combustible component and we have diluents. For example, in solid fuel, the combustible component are carbon, hydrogen and sulfur. They are the combustible component. That means they will combust and release the amount of energy contained in the fuel in the form of products of combustion, whereas diluents, or sometimes they can also call incombustible components, they are nitrogen, oxygen, ash and moisture. So, A stands for ash and M stands for moisture. Whereas, in case of gaseous fuel, the combustible components are say carbon monoxide, then hydrogen, then hydrocarbons. and diluents are nitrogen or carbon dioxide, because they do not take part in the combustion. So, of the fuel, the most important in case of pyrometallurgical extraction is the amount of energy released. Say in case of solid fuel, the amount of energy released by combustion of 1 kg of the fuel and the products of combustion are considered in the reference state, that energy is called the calorific value. So, as such we define one is the gross calorific value. So, we can calculate gross calorific value. Now, in calculation of gross calorific value, the standard state of products of combustion H2O is H2O liquid. So, this can be calculated by a formula, say GCV, that is equal to 339% carbon plus 1427% hydrogen minus percent O upon 8 plus 22% sulfur, you get the value in kilojoule per kg carbon, whereas in NCV the state of H2O is vapor. So, in NCV the state of H2O, that is equal to H2O vapor, where in GCV is state of H2O, that is equal to H2O liquid. So, NCV that is equal to GCV minus 24.44 9% H plus moisture, again kilojoule per kg. Now, I am not going into the details because my emphasis is on the unit process. So, this is just we may be requiring these energy value while performing the heat balance in various unit processes. However, those who are interested, these things I have dealt in my video lecture course on fuel furnace and refractory, very detailed account on this calorific value and analysis all are given. So, you are requested to refer to that, to those particular lectures. Similarly, we can determine calorific value of gaseous fuel, from various heat of formation or heat of combustion value of the products of combustion. Now, for example, let us take a fuel which has a CO that is equal to 30%, H2 that is equal to 40% and nitrogen that is equal to 30%. Now, by knowing the heat of formation value of the CO and hydrogen, because here CO and hydrogen are the combustible component. So, we know that for CO2 minus delta H naught F that is equal to minus 94,450 kilocalorie per kg mole. For carbon monoxide that is equal to minus 26,840 kilocalorie. So, you can determine those. So, we can get the gross calorific value, that will be 0.3 into 67,610 plus 0.4 into 68370, whereas the H2O liquid, the minus delta H naught F, that will be equal to 68,370. Now, since I have written minus delta H naught F here, so there is no need to write here minus or minus, that implies this one. Whereas, H2O gaseous minus delta H naught F, that is equal to 57,801. So, if I calculate JCV, that will come 47631 kilocalorie per kg mole of fuel, because we have selected 1 kg mole of fuel. And similarly, I can calculate NCV, only I have to substitute here for H2O vapor, then I will be getting 4340 kilocalorie per kg mole. So, these calculations we will be needing while performing heat balance in the unit processes that we will be taking. Now, another important thing in case of this combustion is the calculation of air. Here also you will find detailed description in my video lecture course on fuel, furnace and refractory. I am giving a very brief account. So, air, let me say calculation of air. So, air you may use stoichiometric amount, stoichiometric amount is that amount which is required for complete combustion, say C to CO2, H2 to H2O. Also, by observing the stoichiometry of the reaction, whatever amount of oxygen and from there you calculate the amount of air, that is called the stoichiometric amount of air. That means, the stoichiometric amount of air is calculated by following the stoichiometry of the reaction. Any chemical reaction, if you follow the stoichiometry, then you are calculating the stoichiometric amount of air. Now, in several calculation you require to calculate excess air. Now, this excess air, that is equal to actual air minus theoretical air. Now, this theoretical air is also called stoichiometric air, is also called air for perfect combustion. All these names they mean that you have calculated the amount of air by observing the stoichiometry of the reaction, divide by theoretical air into 100. So, we can express, for example, if you say 20% excess air, if we say 20% excess air, then in fact we are using 120% theoretical air. We may say we are using 150% theoretical air, then we can say we are using 50% excess air. So, these are the different names that you will find while solving the problems on the unit processes. Also, we will take composition of dry air, composition of dry air, we will take 79% nitrogen plus 21% oxygen. So, with this 1 mole of oxygen, 1 mole of O2, that is equal to 4.76 moles of air or 3.76 moles of nitrogen, that is equal to 4.76 moles of air, whichever way you want to understand. Now, also the temperature raised by products of combustion is called adiabatic flame temperature, and this temperature can be easily calculated if required for the heat balancing operation in unit processes by doing the heat balance, heat input is equal to heat output. Now, all these illustrations is very detailed given in my video lecture course on fuel, furnace and refractory. Here I have just given a very brief account as required for calculation on the material and heat balance in case of unit processes. Now, here I will also like to give a brief account on, as I have said, that pyrometallurgical extraction also use the so called coke. So, the process of manufacturing of the coke is called coking. In coking, coal is heated out of contact of air and the product which is obtained after heating is called the coke. So, remember, coke is not a natural reserve of fuel. It is prepared by destructive distillation of coal, that is heating the coal out of contact of air. Remember, another term that I have used is secondary fuel, and this secondary fuel is prepared by gasification process. That is, here the coal is converted to a gaseous fuel by using steam, air plus steam. So, the product of gasification will be CO and hydrogen. So, this is just a brief account of the source of energy for carrying out the high temperature pyrometallurgical extraction processes. Now, with this brief account, I will now straightway proceed to the roasting, that is what the first unit process. Now, roasting in fact is a first step to extract metal from sulphide ores. As I have said, sulphide ores are not the sulphide ores cannot be used to produce metal directly by reduction either by carbon or hydrogen. So, first step is roasting is performed, and roasting is say conversion of metal sulphide to oxide partially or completely. Oxide I will write partially or completely, that will depend on type of metal, partially or completely, or sulphate or chlorides, because oxide can be easily reduced, sulphate can be easily dissolved, and that is why the roasting is a first step to extract metal from sulphidic ore. Second, it is carried out, that is an important, carried out below the melting point of the melting point of the components of the ore, That means, you do not go above the melting point. So, as a by virtue of this, the roast product is in solid state. You have ore concentrate in the solid state, so roast product is also in the solid state. The temperature involved during roasting is of the order of 900 to 1100 degrees Celsius. However, it depends upon the various factors. Another important manifestation of roasting is that, say, byproduct of roasting, product is roasted ore or roast product, whatever you want to say, and the byproducts of the roasting, they are SO2, rich SO2, because sulphide ore has 20% sulphur or even 30% sulphur depending on the deposit. So, a large amount of SO2 will be produced, nitrogen and sometimes SO3, all these sulphurous gases SO2 or SO3 can be used to manufacture H2SO4, and if fuel is also used, then you may have carbon dioxide, and and CO is also possible here. Now, certain heating value, say I would like to give you certain heat of formation value, so that you can see that large amount of heat is generated during roasting. Now, for example, Cu2S, it has heat of formation minus 18,950 kilocalorie per kg mole. ZNS minus 44,000 kilocalorie per kg mole. FeS2 minus 35,500 kilocalorie per kg mole. FeS minus 23,100 kilocalorie per kg mole, and then you have SO2, SO3, CO2 and CO. SO2 is say minus 70,940, SO3 is minus 93,900, that is minus 94,450, minus 26,840. However, these values we will be using when we will do the heat balance of the roasting process. Now, various atomic weights that we will use for calculation. Atomic weights, say copper, I will be using 64, iron 56, zinc 65, lead 207, sulfur 32, oxygen 16, carbon 12. I will not be using any fraction. So, these are the things that I am using, and also volume of the gas. Volume of gas I will be expressing, say 1 kg mole of any gas, 1 kg mole of any gas, that is equal to 22.4 meter cube at 1 atmosphere and 273 Kelvin. So, volume of gas at any temperature, volume of gas at any temperature T, that will be equal to V at 1 atmosphere and 273 Kelvin into T upon 273, where T is in degree Kelvin, that will be meter cube at 1 atmosphere and the referred temperature. Now, let us see the amount of heat that is generated by certain roasting reaction. Now, as I said, the roasting converts sulphide into oxide. So, some roasting reactions, say some roasting reactions, for example, Cu2s in condensed phase plus 2O2 gaseous, that is equal to 2 CuO condensed phase plus SO2 gaseous phase. Now, I can calculate the heat of reaction, that will be delta H naught R, that will be equal to 2 into delta H naught F CuO plus delta H naught F SO2 minus delta H naught F Cu2s. So, if you substitute the value, you will be getting that will equal to minus 136,990 kilocalorie. You see that the roasting, a very large amount of heat is generated, and if the caution is not exercised, then there is a chance that the material of the container, it may attain a very high temperature. So, you can see now, let us take another reaction, say roasting of zinc sulphide. Zinc sulphide in the condensed phase plus 1.5O2 in the gaseous phase, you will get ZNO in the condensed phase plus SO2 again in the gaseous phase. Now, here again you have to write delta H naught R heat of reaction, that will be equal to delta H naught F ZNO plus delta H naught F SO2 minus delta H naught F ZNS. Now, here I have not written delta H naught F for oxygen, because the element that is equal to 0. So, there is no need to write. So, if I calculate this, you substitute the value, you will be getting minus 110,440 kilocalorie. So, you note from here that roasting, it can be an autogeneous process. An autogeneous process is one which do not require any heat from outside. The heat which is generated because of the chemical reaction is so high that sometimes you have to do, or you have to cool the you have to cool it so that the temperature does not overshoot. Now, similarly, another product you can have in the roasting of PBS plus oxygen, that may form PbSO4, and its delta H naught reaction, that is equal to minus 197,000 kilocalorie per mole of PbSO4. Similarly, another very important reaction in case of roasting of sulphide ore is the oxidation of iron sulphide. Now, for your information, all sulphide ore, they occur along with the iron. That means, for example, in ore of copper, it has CuFeS2. So, iron is a part of the sulphide ore. So, in almost all sulphidic ore, you will find iron is also there. So, many times the oxidation of FeS or FeS2, that generates a very large amount of heat. So, let us see now, say oxidation of FeS. Oxidation of FeS. So, we can write down 2 FeS plus 3 O2, that is equal to Fe2O3 plus 2 SO2. So, we can write down now here delta H naught R, that is equal to minus 292,000 kilocalorie, this is per mole of Fe2O3. So, you note these are the order of magnitude of the heating value that will be generated during roasting. Now, let us see now the type of, let us say, types of roasting. The different types of roasting. Types of roasting, one is oxidizing roasting. What I have written, the heat of formation value, say you have oxidizing roasting. Now, oxidizing roasting, you have sulphide plus 3/2 O2 in gaseous state, that is equal to metal oxide in the condensed phase plus SO2. Now, for example, I have ZnS plus 1.5 O2 in gaseous state, here this is the condensed state, that is equal to ZnO condensed plus SO2, this is gas and this is gas. Now, in carrying out the essentially oxidizing roasting means you take a sulphide ore and pass air, you provide an oxidizing atmosphere. So, you have to control the amount of oxygen, so that the formation of metal sulphate, it does not form if it is not required. So, in this oxidizing roasting, many times metal sulphate may also form. Metal sulphate may also form. Now, when metal sulphate form, then high temperature is required. High temperature is required to break up the sulphate, Now, suppose you have supplied large amount of oxygen, then PbS is converted to PbSO4 in addition to PbO. Now, whatever amount of lead that has gone to PbSO4 or zinc to ZnSO4, that has lost. So, normally you require high temperature to break up the sulphate. So, therefore, sulphate formation sulfate formation should be avoided, when the extraction of metal is done by pyrometallurgical means. However, if the extraction of metal is done through hydrometallurgical means, then sulfate formation is required, because sulfates are easily soluble in the solvent that you are going to use. Now, another important say roasting is called dead roasting. It is called dead roasting. Now, the term dead roasting means when all sulfur is eliminated and entire sulphide is converted to oxide, this is called dead roasting. So, in dead roasting, all sulfur is eliminated. That is called the dead roasting. Another type of roasting is chloridizing roasting. Chloridizing roasting. Now, as the name suggests, the objective of chloridizing roasting is to convert a sulphide into chlorides. So, the reaction could be a 2 NaCl, NaCl is normally used, plus Ms, that is the sulphide, plus 2O2, that is equal to Na2SO4 plus MCl2. This is, you can call this is a direct chlorination. Another is the indirect chlorination, where you use a reducing agent, that is 4 NaCl plus 2 MO plus S2 plus 3 O2, that is equal to 2 Na2SO4 plus 2 MCl2. So, chloridizing roasting is done to convert a sulphide into chloride or oxide also into chloride. That is what the chloridizing roasting. Now, another roasting is also called sulfatizing roasting. Sulfatizing roasting. Now, as the name suggests, in the sulfatizing roasting, the objective is to convert sulphide into sulphate, and this is particularly required when you extract metal from hydrometallurgical means, because in the hydrometallurgical means you want that the metal should be dissolved, and sulfates are easily soluble as compared to sulphides. Another important method is sinter roasting. Sinter roasting. Now, in sinter roasting, what is done? The partial oxidation I mean, as roasting is what partial or fully oxidation plus modification of the physical condition of the ore, plus modification of the physical condition of the ore. Physical condition of ore, that is called sinter roasting. It has come from two words, sinter as well as roasting. Roasting means oxidation and sintering means you want to, for example, decrease the porosity of the sinter product. For that you again heat up, and that process is called sintering. So, that is called the sinter roasting. Now, in fact, both this sinter roasting oxidation plus sintering. Now, let us see some of the roasting technologies. Roasting technologies. Now, what you require? All that you require an ore concentrate, that is a mechanism of feeding of ore concentrate, then mechanism of supply of air, because you want an oxidizing medium, of course, you require a container, and then a mechanism of output of the roast product, and sometimes roast product is also called calcine, and mechanism for the discharge of the gases, that will in short be comprised of the so called roasting reactor. So, for that now here one can think of, you create a bed of ore concentrate, allow the air to flow and let the roasting carry out in a fixed bed, or you allow the particles to react with air. So, there could be several ways in which the ore concentrate is supplied to an oxidizing medium. Now, say for example, in fluid bed roasting, say ore particles are roasted, while suspended in an upward stream of gas, Now, you mind you, this mechanism will have a very high reaction rate, because the particles will be suspended directly in the air and very high surface area is exposed. So, a very high reaction rate can be observed. So, in the fluid bed roasting, for example, something like this, it can go, say this one is for say hot gases, discharge of hot gases, and somewhere here the discharge of hot calcine, you call hot calcine or roast product, they all have this, and then we have say from here, if some fuel is required for some purpose, then there is a provision of supply of the auxiliary fuel, and so here you have the feed, and somewhere here this one, and you supply air. So, the particles are roasted while they are in suspension, and this one is called a distributor, because when air is supplied, it distributes the air, so that the particles get sufficient amount of air. And here sometimes what is been done, the temperature goes very high. So, here water spray for temperature control, This is one of the method of fluid bed roasting. Now, in fluid bed roasting, the heat losses are relatively small, but the temperature can rise to a very high value. There are two ways, either you have a water spray, or the excessive temperature is controlled by controlling the excess amount of air, because when you use excess amount of air, the nitrogen will take away the necessary heat, and so you control the temperature. This is one of the method. Another method is, say for example, flesh roasting. Another method is flesh roasting. Now, in flesh roasting, the finely divided sulphide concentrate plus air, that is a mixture of both, is passed in a reactor, and there occur the roasting. So, that is for example, this is the reactor. Here the roast product, this is the discharge of the gases, and here this is a mechanism, this is a mechanism which rotates, and here the feed which consists of concentrate and air. So, here and here you have the finally divided sulphide concentrate plus air. Here roast product is out, and this is in fact the combustion chamber. And this rotates to make the easy discharge of the roast product. So, this is again another type of method. There are still other method, multiple hearth roasting and so on. The details can be seen. I will give the reference towards the end, so that you are aware the methods, because the whole my objective of this presentation is only to make you feel what is the roasting, so that when we do material and heat balance you are aware what roasting consists of. Now, after having seen these various aspects of roasting, now what is important in case of roasting is to know what phases can form. What phases can form. Say we have metal sulphide to start with, and we supply the oxidizing air. There are several phases can form depending upon the partial pressure of oxygen in air and partial pressure of SO2. Phases like sulphate, oxide, metal and intermediate oxides or sulphide, anything can form. So, the question comes, what phases can form? Suppose if you want to control the process of roasting, you want a particular phase for a particular method, so that pyrometallurgical extraction become easier. How to control these phases? So, the control of the phases or the prediction which phase can form, it can be done under equilibrium condition. With that I mean, say if we consider a system, for example, M, S and O. M stands for metal, M for metal, S for sulphur and O for oxygen. Say if we consider MSO, this is a system metal, sulphur and oxide, then prediction of phases, it can be made by doing certain thermodynamic calculation for formation of different products. That means, what we should control, what parameters should be controlled, so that a particular phase is formed, and this information can be obtained from phase rule. I hope all of you must be aware by phase rule. That is, which parameter can be controlled, so that a particular phase forms, this information can be obtained by phase rule, and phase rule we have P plus F that is equal to C plus 2, where P is number of phases, F degree of freedom, and C number of components. C is number of components. Now, this 2 is coming because here temperature and pressure are the factors or the thermodynamic parameter that will control the roasting process. Now, in the condensed phase, pressure has no effect. So, we can consider the modified form of phase rule P plus F that is equal to C plus 1. So, now here the temperature has remained a controlling factor. Now, suppose we consider at constant temperature, because normally roasting is carried out at constant temperature. So, at constant temperature, what will happen? We will have F that is equal to 3 minus P. 3 is coming because number of components are 3, M, S and O. So, now F, the number of degrees of freedom, that is equal to 3 minus P. So, if we have P is equal to 3, then degree of freedom that is equal to 0. If we have P is equal to 2, then degree of freedom is equal to 1, and if we have P is equal to 1, then degree of freedom is equal to 2. That means, in this particular representation, when we have taken a constant temperature, then PSO2 and PO2, these are the two variables that will control the formation of which phase at a given temperature. Mind you, in deriving this, we have considered temperature to be constant. So, when you want to get the information of which phase will form, then it is the PSO2 and PO2, both these parameters will decide, and based on this, if we perform the thermodynamic calculations of the various equilibrium reaction that can occur between sulphide and oxygen, then we get a diagram which is called predominance area diagram, From the predominance area diagram, one can get the information what should be a combination of PSO2 and PO2 at a given temperature if we want a particular phase. That will be a subject matter of next lecture.